Part E of Module 2, the last part, more exercise questions. In this part, I like to give you as many examples as possible because during the part A, B, C, D, we did not have much time to do some exercise questions. So then we need to do plenty of exercise questions in this part. All right. E.1, exercise questions set number 4. Now, I have 4 questions here. Now, first, look at our first question. If an algorithm does not perform well for small input size, small input sizes, because we could have several different sizes, small input sizes. All right, then we cannot say that this is an efficient algorithm. Answer is false. So why? The problem is here. For when we consider input cases with relatively small sizes, then the overhead takes a big role. Yeah. So what is the overhead? What do you mean overhead? Preparation part. When we work on a problem, when we, prepare ourselves solving a computing problem, we need to do a lot of preparation. We need to set up the environment. We need to prepare our data. So we need to do a lot of preparation things. That takes a lot of time. Okay? Yeah. So that part we treat as the overhead part. When the problem size relatively small, then the overhead part takes a significant portion of the whole execution time. Okay? In execution time. That get efficiency distorted. Get efficiency distorted. So we should not look at the, whatever the behavior it is for the small input sizes. All right. So we should mainly look at the problem size. So the problem size sufficiently large. This sufficiently large, this wording looks a little vague. Here, we need to use that vague wording. The reason is we don't know the exact amount for the problem size. That point can vary for different problems. Yeah. But whatever it is, we should consider problem. When we look at the efficiency, we should consider the problem size sufficiently large. In our asymptotic notation, we use n0, so we only look at the n values that is greater than some reference number and 0. Yeah. All right. So this is the explanation, our first question. Our second question. Compare efficiency of two algorithms through their growth functions. Suppose the first algorithm with this first growth function, second with the second growth function. Which of the following growth functions corresponds to a faster algorithm? First, let's think about the smaller the growth function, the faster the algorithm, right? Yeah. So we like to find the smaller growth function because that corresponds to faster algorithm, not the opposite. All right, yeah. Here, first, conclusion, this is smaller. Not first one. Yeah. But I feel some of you may pick A because when they see 1.01, this is a very small number. Even if you raise to nth power, based on their intuition, they feel that could not be increasing very fast, but actually it's not. In this situation, your intuition may not be very reliable. It could be wrong. So our intuition, sometimes it could be wrong. Here, that's a case. If you do not have enough experience, you may get it wrong. All right, so here, let me remind you, there is one example we learned in part C. Example, that part. All right. We learned n to the dth power belongs to little o of a to the n with a greater than 1. Do you still remember this? This tells us if you take the limit, n goes to infinity, n to the dth power, d is some positive number, not necessarily integer, but here it's an integer, right? Here it is 100, okay? And a to the nth, but we need a greater than 1, this limit equals to 0. We proved that. Remember? We proved that. We used the L'Hopital's rule. First, we need to convert it to continuous variable, right? Because here, this is a discrete variable. We need to convert it to continuous variable x to the dth power, a to the x. Yeah. Then we can take L'Hopital's rule, and then we can find this answer. After that, you can see where n is sufficiently large. Here you can see we like to use that vague wording, sufficiently large, because even 1 million, 1 billion, n0 equals 1 million, 1 billion, it is okay, right? So you can imagine so the 1 million, right? 1 billion that could be the number, the line we start with, sufficiently large line. That line we can take, okay? Yeah. No matter it is, how much it is, there is some number there, okay? So when n is sufficiently large, a to the nth. So here, a equals 1.01, that is greater than 1. No problem, right? Yeah, that condition is satisfied. So we can use this result that tells us a to the n dominates n to the 100. In other words, n to the 100. Eventually, this function will be smaller than the other function. The smaller the growth function, the faster the algorithm. So that's why our answer is B. Yeah. All right, so next question. Number 3. The 11, that means our total number of questions, total order, total question order. Yeah, because for this class so far, this is our question number 11 in all the exercise questions. All right, so here, this question, is it true that B parenthesis n plus 1 over n parenthesis cube belongs to big theta of cube? Yeah. By intuition, it is true, right? Yes. Yeah. But I need to explain why it is true. Yeah. The simplest way, using the limit. Here, limit is the fastest, simplest way. Why? Here, let me give you one experience. When you see big theta, when we need to show, one function, f function, belongs to big theta of g function. Yeah. When we see that big theta, 90% of the time, I do not say 100% because there could be some special cases. Okay, 90% of the time, the limit way would work. The limit way would solve the problem. Very nice. Yeah. Let's see. Let me show you. Let's do the limit here. N goes to infinity. The numerator n plus 1 over n cube over n cube. All right. Let us do transform. We need to do transform so we can see the result easier. Limit n goes to infinity. Can we write n plus 1 over n cube? Because numerator cube, denominator cube, can we take the common cube out of the big parenthesis containing both numerator base, denominator base, right? We can do it. Yeah. That simplification. N goes to infinity. Inside the big parenthesis, 1 plus 1 over n squared cube, right? 1 over n squared cube. This time, now, it's easy to see the answer because 1 over n squared goes to 0 when n goes to infinity. 1 plus 0, that's 1. 1 cube, that's 1. See? The ratio, when n goes to infinity, the ratio of those two functions is 1 non-zero constant, right? Non-zero constant. That means big theta notation. Big theta relationship between these two functions. Okay? All right, so that's our third question. The last question of this part, number 4, which of the two functions log of n and n to the 1 over nth, the exponent part is 1 over n, grows faster. Grows faster, that means the function smaller, right? Yeah, smaller. The smaller the function, the faster the, oh, sorry, be careful. Oh, here, grows faster, the larger the function, right? Yeah. So here we need to distinguish these two cases. Okay? Yeah. Function, yeah, it's very easy to get confused. Function grows faster, and the algorithm runs faster, right? So these two things completely different and opposite. The relationship opposite. Okay, opposite. Here, which is the case we need? Yeah, two functions. Which one grows faster? This one. So that means larger, right? So eventually, the function value is larger. We need that case. All right, so let's take a look. Yeah. First, this function relatively harder to see, how fast it grows, right? Yeah, because we like to see what is the limit n to the 1 over nth. We like to see it. But for an exponential function, both base part and the exponent part contain the variable. That makes the whole thing pretty complicated. So there is a commonly used method. We let y be the whole thing. How about that? If we introduce a new variable y, new symbol y, representing the whole function, then we can take a logarithm. Natural log of y equals natural log of n to the 1/nth power, and by logarithm property equals n, right? So that means natural log of n over n. Can we see the limit of this when n goes to infinity? Right? Can we see when n goes to infinity y, that equals n goes to infinity natural log of n over n. We did that before, right? Compare log function with polynomial function, because this, or power function, and not necessarily polynomial, right? Because remember, n to the dth. Yeah. Compare the power function, d positive. When you consider that limit equals 0. All right? So that means when n goes to infinity, y value goes to 0. Oh, sorry, not y value goes to 0. Log y goes to 0, right? Natural log y goes to 0, right? Yeah. Natural log y goes to 0. So then y equals e to the log y. E to the natural log y, right? Yeah. By the definition of log. What's the definition of log? Log, when we go back to the base function, go to the, that function part, the log base, exponent base, we use e. Yeah. So e to the log of n, the exponent goes to 0, so that goes to e to the 1, or e to the 0, that is 1. Okay? So that means this limit equals 1. When you compare 1 and the log of n, which one is larger? Okay? The function goes faster, a function goes faster, because b function goes to constant 1. Goes to constant 1. Okay? Yeah. Here we just use natural log. Take a limit. After we get limit is 0. Then we go back to the original function. Yeah. But the original function, the key part is we need to write an e to some log n. Okay? Yeah. So y equals e to the, we need to write this way. Can you see that? Can you see that? Okay, yeah. So this expression here, you need to be familiar with this one. Okay. Later somewhere in this part E, I will explain another formula. So what's that formula? Okay. So that the formula is y equals a to the log base a y. So the log base here, exponential function base here, if they are the same, then these two expressions are the same. Okay, so later we'll look at this more general formula. Here, that A equal to E. Yeah, so we have this version. All right. So that's all the questions for part E.1.